In this chapter, we will look at the laws of friction, static friction and kinetic friction, and do a simple illustrative experiment. I will make you a solid prediction and say it with lots of conviction. From good analyzing, you'll see things surprising regarding the true laws of friction. At the end of the last chapter, we talked about not being able to stop the bike using the brakes when it goes into a skid. And that will depend on the friction between the tires and the road surface. If I simplify this picture by just taking the hill out, then the braking force applied by the road surface on the front wheel is the force here that we worked out in the previous chapter. And that is the force exerted by the road surface in the X direction opposing the forward motion of the rider. And that force comes from friction between the road surface and the tire. First, one caveat here about the laws of friction may be in order. Some people will say these are not true laws because they lack the mathematical rigor of, say, Newtonian laws of motion, but they are nevertheless excellent approximations in many cases and are very useful for our discussion of bicycle physics. So these are the so-called laws of friction. I'll list them for you and then we'll go through them one at a time. For a moving object, friction is proportional to the normal, that is, perpendicular force. The coefficient of static friction is greater than the coefficient of kinetic friction. Within large limits, kinetic friction does not depend on velocity. Friction depends on the nature of the two surfaces that are in contact with each other, and friction is independent of the contact area between the two surfaces. A says that for a moving object, friction is proportional to the normal or perpendicular force. Here we see a wheel and there is weight on the wheel. The weight is equal to the mass times the gravitational constant. Opposing that is an upward force, which is called the normal force. B, the coefficient of static friction is greater than the coefficient of kinetic friction. The Greek letter mu is the coefficient of friction. Let's focus on just one wheel. Static friction is the force between the road surface and a rolling tire. The forces of attraction between the tire and the road surface are typically very strong. As the tire rolls, these forces of attraction have to be constantly reformed and rebroken. Kinetic friction is the force between the road surface and a skidding tire. The friction between the tire and the road is greater when it's rolling than when it's skidding. And static friction is what is most important to us anyway, because we would rather slow or stop the bike before it goes into a skid. C, within large limits, kinetic friction does not depend on velocity. In terms of kinetic friction, these two are equivalent. D, friction depends on the nature of the two surfaces that are in contact. We ask ourselves, what factors does the coefficient of friction depend on? The coefficient of friction is a function of many variables, and you will find this to be pretty intuitive. The first of these is the tire type and construction. Some tires are simply made of stickier material than others. Ambient and surface temperatures. Adhesion between the tire and the road is going to be greater on a hot day than on a cold day. Likewise, when the tire is hot or the road surface is hot. My surface could be asphalt, concrete, or dirt and gravel. And my surface condition could be dry or wet. It can be useful to go to the websites of tire manufacturers and see what data they provide. We're going to be content here to look at this conceptually because it's quite complicated, and if we start delving into it, we may never get out of it. But if you're interested, I invite you to do some research on your own. and we'll take a stab at approximating the effect of the surface and the surface condition. For what it's worth, I did find the following information from the website shown at the bottom. For friction coefficients based on road tire characteristics, the first bit of information we find is this. This tells us that for a bicycle tire, under the conditions of dry asphalt or concrete, I have a friction coefficient of 0.75. The website did not give me a friction coefficient for a bicycle tire for wet asphalt or concrete, but it did for a car tire, so we're going to figure it out for a car tire and then infer what that would be for a bicycle tire. For a high performance car tire under the conditions of dry asphalt or concrete, I get a friction coefficient of 1, which is pretty much perfect adhesion. My high performance car tire under conditions of wet asphalt or concrete will give me a friction coefficient of 0.7. For my car tire, my friction coefficient under wet conditions is 70% of the value under dry conditions. We can make this leap and say that, therefore, for our bicycle tire under the conditions of wet asphalt, the friction coefficient is going to be 0.75 times 70%, which is 0.53. Let's just make it an even 0.5. Going back to this picture, let's insert the normal force, which is pushing up on the wheel and opposing the vertical acceleration of the wheel or the weight due to gravity. The Greek letter mu is commonly used to designate the coefficient of friction, and the braking force is equal to mu times the normal force. If the coefficient of friction is 1, I get the full benefit from my brakes. If my coefficient of friction, however, is 0.75, such as a bicycle tire on a dry road, then my braking force, instead of being this amount, is only 75% of that. And my bicycle tire on a wet road would see the braking force decrease from this to this. The last of these, that friction is independent of the contact area between the two surfaces, is probably counterintuitive and requires some in-depth explanation. Let's do a little experiment using this table. We put a pulley on the end of the table and a brick on the top of it, and then we're going to run a string around the pulley attached to a weight and see how much weight is needed to make the brick start to slide, thereby overcoming the static friction between the table and the brick. Here's a picture of my brick. The force on it is mass times acceleration. It's 2 kilograms times the acceleration constant. That gives me 19.6 newtons or 4.41 pounds, and that is the vertical force pulling on the brick. Whether I have this face here on the table or this face, the weight necessary to make the brick begin to move will be the same. These are the dimensions of the brick in inches. So the area of this face is 40.5 square inches. The area of this face is 22.5 square inches. And the area of this face is 11.3 square inches. So when I divide the weight of the brick by the area of the contact patch of the brick with the table, I get these numbers of pounds per square inch. If we could see into the side of the brick, we would see that the force of the brick pushing down on the table is equal to the force of the table pushing up on the brick. Let's look microscopically at the surface of the table and the surface of the brick where the two surfaces come together. Microscopically, the rather coarse brick might look like this with sharp points sticking out underneath it, and the rather smooth table might look something like this with much smaller sharp points. In material science, these points are called asperities. The weight of the brick pushes these two surfaces together, and the attraction between molecules of the brick and molecules of the table gives us friction. When the brick is oriented with this surface pushing on the table, then the force per unit area is given by the pressure, which is 0.11 pounds per square inch. The surfaces are pushed together limitedly, and this yellow line here marks the extent of penetration of the brick into the table. If I have this side of the brick facing down, I have the same weight now exerted over a smaller area. The brick pushes itself a little farther down into the table. With this side facing down, I have the same weight exerted over an even smaller area, giving me this picture. Here's a different view of the brick with its largest face pushing down against the table, and its smallest face. Looking at the table on the left, force X will be required to break the static friction and cause the brick to begin to slide, and on the table on the right, with the brick oriented differently, nevertheless, force X will again be required here. I want to show you the summary of a result of an experiment done by a couple of guys at Flow. We start with two identical cyclists. The force on the front wheel is 65 pounds or 289 newtons in each case, and we can show that this way. And now we're going to load two tires that start with a pressure in one case of 80 pounds per square inch and the other 120 pounds per square inch. As a reminder, we're talking about friction here, and so this is not a discussion about the benefits of using a wider rim and a wider tire and riding at somewhat lower air pressure. The red lines around the tires are there just to define the perimeter of them. The tires deform under the force of 289 newtons that are pushing them down. Here are the dimensions of the elliptically shaped contact patches that form. The contact patch on the right with the tire at 120 psi is both shorter and narrower than the one on the left. These are the areas of the contact patches both in square inches and square millimeters. I want to look at the pressure, not of the air inside the tire, but right here where the tire makes contact with the road. The pressures are gotten by dividing the weight on the front wheel, which is 65 pounds in both cases, by the contact patch areas, which are not the same. The tire on the left with a larger contact patch area will give me a smaller pressure. The tire on the right with a smaller contact patch area will give me a larger pressure. And here it is in pascals if you want to see it that way. To a very close approximation, the static friction of both of these pictures will be the same. The next few graphics will give you another example of the difference between rolling tires and static friction and skidding tires and kinetic friction. This is the wheel with the tire installed and the road with less magnification. We'll call this point a tooth and this point a valley. The tire has weight on it because of the mass of the rider on the bicycle. The tooth pushes itself down into a valley until the normal force pushing up equals the force pushing down. If we magnify this area here, we will see something like this, and the forces of attraction between the tire and the road surface give us the static friction. Chemically, these forces of attraction are between molecules in the tire and molecules in the road, and they are called intermolecular attractions. Water on the surface of the road will cause a small upward pressure on the tire and not allow the asperities to penetrate quite as deeply as they do with a dry road. Additionally, water on the surface of the tire and the road will weaken the intermolecular attractions. As the wheel rolls, this tooth here that will mark moves to this position, and then this position, and so on. What's important to grasp here is the following. Even though the tire is rolling, the instantaneous velocity at any point is zero. Therefore, the forces that we're dealing with are static, not dynamic. In each case, new forces of attraction arise and have to be broken all over again. So the static friction continues in every position. As the wheel turns, these normal forces will move with it. And we see this. This is the scenario for skidding, where the tire is not penetrating the road surface. I still have these opposing forces here, but the tire is not turning, and I'm not getting penetration of the tire into the road surface, so the forces of attraction are not as strong. The tire skids rather quickly across the surface of the road. Actually, there is a little bit of penetration of the tire into the road, and we'll go back to our blow-up diagram and see what that looks like. Here we are again, and I'm going to mark the top of the asperities of the road surface with this black line, and we'll get rid of some of these other lines too. Now we can more clearly see what's going to happen, and perhaps you can see that as the tire slides forward, the tips of the harder asperities of the road will slice off the less hard asperities of the tire, leaving us with these little tips. Let's make them black so that we can see them better, which in 3 dimensions perhaps looks like a skid mark, or as seen here. Let's go back to this table, show some forces on the brick, and then plot a graph. Here is the downward force of gravity on the brick, the opposing normal force. Over here is the applied force on the brick, which we can show here, and the opposing and equal force of friction. We'll plot a graph on the x-axis, the applied force, and on the y-axis, the opposing force of friction. In this first picture, these forces are small and we get a short line. As the forces get larger, the line gets longer. A still larger applied force and still being opposed equally by the force of friction. However, I've reached the limit of my force of friction, so any increase in the applied force will result in the line here not going up, but actually dropping down and then going sideways, indicating that the brick is sliding. This line represents the maximum of static friction, and this point is that maximum being equal to the coefficient of static friction times the normal force on the brick. This equation down here, the force of kinetic friction is equal to the coefficient of kinetic friction times the same normal force on the brick. In most cases, the coefficient of static friction is greater than the coefficient of kinetic friction, and it might be a lot greater. In the straight line part of this graph, it's clear that the static friction is proportional to the applied force, so we really are looking at the slope of this line, and the slope of this line is the coefficient of static friction, which is also the proportionality constant. Of course, the slope of that line, mu, can vary widely depending on what the surfaces are. I will show you some examples from the Handbook of Chemistry and Physics. We'll make a little table of material 1, material 2, the conditions, and then the static and kinetic friction. Here are some examples. Hard steel on hard steel in both cases, but the conditions are different. One, there's lubrication and different values, lower values, with the case of the oil for both coefficients. Aluminum on mild steel and brass on mild steel, both dry conditions, different coefficients. This next one's particularly interesting because in both cases we have oak wood on oak wood under dry conditions, But the first one here, the grains are parallel, and in the second one, the grains are perpendicular, and that means that the intimacy of the contact between the two boards will be less, and the coefficients are less with the perpendicular configuration. And lastly, we have glass on glass and glass on nickel. So you see there are many variables in the results. Let's conclude this discussion by going back and taking another look at the tire type and construction that we just touched on before. We can look at static friction, rolling resistance, durability, and cost. But if you're rich, maybe you don't care about the cost. But we still want to achieve a balance between static friction, rolling resistance, and durability. I could use a tire made out of stickier rubber or softer rubber. Either of those will make mu increase, but my rolling resistance will increase as well, and the durability would decrease. That may be a very reasonable trade-off for mountain biking. The ultimate example is probably the tires on a Top Fuel dragster, which certainly are sticky and soft, and they spin them to get them hot, but the durability is very small, lasting about a quarter of a mile before they change them. But for a racing bike, I need durability and I need low rolling resistance, and I'm going to be willing to accept a harder rubber with a somewhat lower coefficient of friction. This topic of rolling resistance is very interesting and also very involved, so we're going to talk about that separately in a later chapter, but that will be after discussing some other things first, notably aerodynamics.